Okay, so I think it would be absurd to do a whole algorithms class and not teach you hash tables, seeing that this is the workhorse of so many basic things. So we'll do some hashing today, and we will do hash tables. And I don't know how much of this we'll cover today, but I'll give another application of hashing that's not exactly hash tables, but still pretty cool. So hopefully it'll kind of expand your imagination in terms of what hashing can do. So good. Um, right. So this will be, I think, our last lecture about randomized algorithms in any form. So, all right, let's first talk about hash functions and what they are, or the applications. Okay, so how many of you have seen this web page? Yeah, I've read this like a million times. So this is a Python, I guess, documentation about dictionaries, right? And what's interesting in Python, this dates back to Lisp, is that dictionaries are given as a primitive, right? They're not like some weird library you call it. There's a notation for it, and you just use it all the time. In fact, do you know how objects work in Python? They're just dictionaries, okay? And the class structure, you make some kind of prototype of the instance. And when you make a new instance of the class, you just copy and paste a dictionary and you work from there. Okay, or you start a new dictionary with like a parent pointer to the class dictionary. Okay, so that's how they do it. You know, there might be some cases where the compiler can do a little extra, but that's how it's designed. So you know, you all probably grew up in the Python era, so you're just used to having dictionaries like automatically. How many of you have seen this web page before? Yeah, yeah, how about this? What language is this for? So who thinks it's C++? Or thought for a moment at least, just for fun. Yeah, it does say Java when you look closely. Um, yeah. So this is the Java documentation for an interface of a key value map. It's Java, so you actually everything is typed k comma v. So Java is actually a bit annoying. Well, a lot of things in Java are a bit annoying, but you actually have to you have to import some stuff to actually use a hash map. Okay. So, but also when you do Java, like this ends up becoming a workhorse as well, even if it's a little bit more notationally cumbersome. In fact, yeah, I mean, at least my brief experience in the real world was like, no matter how brilliant your designs for your original object system, you think you're going to map out everything, all systems over time are going to converge to just passing around hash maps with just strings to strings. Okay, you're just going to be passing massive property dictionaries around, and it won't matter what you thought you were going to do on day one, right? Because they're very versatile. They're very easy to extend. You don't have to rebuild your whole system when you add a new field. All these kinds of things. So there are good reasons for this, and you definitely can't see this at the bottom. They actually give a couple different things to implement it. So hash map, tree map, hash table. Don't ask me exactly the difference between a hash map and a hash table. I guess a tree map will probably be like a binary tree kind of thing. A sorted map, I guess, probably has the keys in sorted order, which should be implicitly very similar to a tree map, but anyway. Okay, so so you all know this data structure probably really well, you know, the idea of a dictionary or something. So we're just going to simplify things to only have three operations. I want to insert a key value pair, delete any value associated with a particular key, or here's a key, what's the value associated with it? Right? So dictionary or a map, very versatile data structure. So, okay, so how do we implement these things? Well, there's different situations. So let me start with a special one. So in general, you want to maintain, you know, key value stuff, right? So suppose all the keys were a set of contiguous integers between 1 and n. Okay, that might sound kind of special. But in fact, that's sort of always been the case for everything you do. If I give you some kind of graph problem with m edges and n vertices, the first thing you can do is just number the vertices 1 through n, refer to them with 1 through n from now on, and that'll just be an index into, potentially this table. So in these static settings where, all the keys are known up front, which is the case for almost all of our problems so far this class. In fact, this could be the case. But anyway, if you're in this kind of situation, what would you use? So if your keys are just integers from 1 to n, and you know that ahead of time, what would you use to implement a dictionary? An array, right? An array is like the best possible thing. So you just have an array, you allocate n slots, and you put the n values there, right? You're going to use the bare minimum amount of space, big O of n, and you're going to be able to access things in constant time. Okay. All right. So an array is perfect. What's the weakness of an array? Yeah, what happens when you decide you will have n plus 1 keys, right? If it's not so static. Then, in fact, arrays can be quite brittle. Um, right, so it's perfect in static settings. Another one is you just stop using key number 4, key number 5, key number 10, and things like this, and you start getting lots of holes. And suddenly your data structure isn't very compact anymore. What seemed like O in space where n was great, n went down to something much smaller while your space didn't change. Right? So good. So here's a setting that would give it a hard time. So this would be like a very sparse setting. So our keys may still be integers, but now the range of integers is ginormous. Okay, between 1 and u, where u is effectively infinity. Okay. So a simple example is that you have strings, right? And I can take a string hello and write down the ASCII numbers and interpret that as a ginormous, number. Okay. Um, and so I just want to store, a dictionary almost in the common sense of the word. So so in this case, right. So in this case, what? How much time would an array take for a basic operation? If I was using an array for key value? Yeah, still O1. So actually, the running time would be great, but the real issue is what would the space be if we just kind of took the previous approach? How big an array would you need to allocate? Yeah, something proportional to the set of all possible keys, which is problematic because that's a much bigger number of keys you actually have, right? So we want some solution that's more like big O of n. Okay. Now, setting aside hash tables, which you've heard of, we're going to get to a moment. What would be a different data structure that could try to address this space issue? Sorry? Oh, okay. So if you did an array list, looking up is going to, okay, an array list is still going to be an issue. So if I just had key 1, key corresponding to the first possible integer, and key corresponding to the last possible integer, you're going to make a massive array list to span it, right? So the issue is you have all these zeros in the middle. So what else? Yeah. Oh, okay. So a linked list, I can make a K1 points to K2, points to the next key, points to the next key. But then you're going to take a little while to have to scan to find it. What's something in between these two options? A tree. So especially that's one that's automatically balanced, like the lazy trees we did, or many other options. So this is going to take O(n) space, which is great, right? So you're going to have basically one node per key, or if you're doing some kind of tree where the keys are only at the leaves, you still know you're only going to have big O(n) nodes because everything will have degree 2 above it. But how long, assuming it's a balanced tree, you have a good tree data structure, how long will one of these operations take? Okay, log n. I think like 10 people mouthed it. Okay, so it's going to take log n time, right? So this is sort of the situation then. So arrays get you ideal time, but are space inefficient. And trees have perfect space usage, but they're a little slower than arrays. Okay. I know I often don't stress logarithmic factors in this class, but on this topic, people do care. Okay. And so the big question that we're going to address this lecture is, can you get the best of both worlds? Okay. Can you get constant time and linear space, or constant per item space? Okay. And so the answer, as you have probably anticipated, is yes, but with randomization. Okay, so we'll need to use randomization to get this best of both worlds performance, right? And as you already know from experience, the outcome will be rather practical. So, okay, so we are going to leverage hash functions, okay? So hash functions aren't random functions. They're slightly different. They're randomly constructed functions, okay? So when we make the function from 1 to n to 1 to k, when we make it, we use some randomization at that point in time. Like we randomly initialize it with maybe be the ML-ish terminology, and then it'll give you, just a function. Okay, so I'll give an example in a moment. Now, for everything today, this is not always the case, but often the case, n is going to be the relatively big number, and k is going to be the relatively small number. Okay, so n would probably correspond to that big U from before. K would correspond to maybe something closer to the number of keys, n from before. And I mixed the notation just to give you a hard time. Okay, so, you have this big set of possibilities n, a smaller set of outputs k, okay? And what you want to do is your function wants to map from n to k. And in principle, you want sort of the destinations to all look pretty random. Okay, so like any particular slot up here, you're hoping can land in any particular slot down here. Okay, so that's the high level idea. So an ideal hash function, okay, an ideal hash function would be one where for every possible input, it has a uniform chance of being any possible output, and it will be completely independent of each other. Okay, so if I actually constructed H by saying, okay, for the first one, I'm just going to roll a dice between 1 and k. Second one, I'll roll another dice between 1 and k. Right? And that was how I constructed the function. That's as random as possible. Okay, we actually want more randomness in this because it's going to be kind of smoother. Okay, so that would be an ideal hash function, and often this is the easiest to analyze because, from an analytical perspective, we like things like uniformly random and independence. Right? If there's no dependence, then everything is very easy to look at. Okay. Now, this is still often a good working prototype when you're coming up with algorithms, but there's one basic issue. Okay. Does anyone see an issue with from an implementation perspective? There's a practical issue with this. So collisions can't be helped no matter what, right? Because you're going from big to small. So collisions can't be helped anyway. I'm worried about the ideal aspect. What was another suggestion? Yeah. So we're already committed to this mapping down thing so that ultimately we can use smaller space down below. And that's almost a feature for us. Okay. No, it's a little bit more subtle. So, are any other suggestions? Okay. So, how much space must an ideal hash function from 1 of n to 1 of k take? So a naive version is I write down all n numbers, right? So that would take like maybe n log k if each of these indices out of k need a log k bits or something, or roughly n. Okay, but I want to argue that it's actually hard to do much better than this. So if this required like roughly n space, that would be bad because n could be ginormous, right? Because n is like the size of our universe. Okay, but how can I argue that writing down ideal hash functions would require that much space? Okay, here's a baby question first. So an ideal hash function can output any particular function from n to k, right? They're all possible. Maybe with small probability, but they're all possible. How many functions are there from 1 of n to 1 of k? K? It's going to be a lot more than k. Sorry? Nk? It's going to be actually much bigger than nk. N choose k? It's going to be even bigger than that. Actually, n choose k, which is roughly n to the k. But you're getting closer. You're also getting bigger. So that's also automatically getting you closer. So, what defines one of these functions, right? Well, you have to choose a number between 1 and k for number 1, right? So that's k choices. And you have to choose a number between 1 and k for number 2. So how many choices is that? That's k more. So far, you're already up to 25 choices, k squared choices. Okay. So k to the n. There's k to the n possible functions from 1 of n to 1 of k, because each one is choosing one of k things. And so you get k to the n as opposed to n to the k. And okay, good. So all I know about this is that any function is possible. So there's k to the n possibilities, right? Okay. Now what's the next step? So I'm trying to argue that you need at least n log k bits to express these functions, to write them down. Nope. Yes. Yes. N log k. Yeah, this goes back to sort of our searching lower bounds from the beginning, right? So, or sorting lower bounds. If there's k to the n possibilities, right, you need log of k to the n bits to write them down. Because if you have 100 bits, you can only express 2 to the 100 different things, right? L bits, you can only express 2 to the L different things. So taking the logarithm of this tells you that you actually need n log k space in the worst case. Okay, and n for us is ginormous. K is okay, but n is a major issue. Okay, so while this is nice to think about from an analytical perspective, and when you're coming up with algorithms using hashing, you might on first pass imagine using this. It's easiest to think about, easiest way to generate ideas. We're going to have to get around the fact that, oh, we can't actually generate perfect hash functions just for this basic counting argument. Okay, good. So what people do then, okay, oh well. So what we do then is we generate functions that are going to satisfy some properties of an ideal hash function and sort of just enough to push the analysis through. So what this is presenting is roughly the bare minimum. Okay. So let's say I have n different inputs and it's going into k slots, right? If it was completely random, like the first one maps to this slot, the second one would have a 1 in k chance of colliding. Okay. So I'm going to say, okay, suppose that's all I ask for. Just any function h, okay, where if I look at any two particular inputs, the odds of them colliding is at most 1 over k. Okay, and that's all I'll require of h. That's sort of like an ideal hash function, but not nearly a stronger requirement. So ideal hash function also says like any 3 points, the odds of them colliding are like this and this and this. And all these are any 4 points, any 5 points, right? There's way more constraints for an ideal hash function. This is only worried about pairs. Okay. And if you have such a weak requirement, then actually this function is just fine. Just ax plus b. Okay. So you're just mapping from x, some integer x over. Okay. So there's a little bit of nuance. So you do ax plus b modulo a prime number for technical reasons. Okay. And then you do it modulo k, which is the size of the array you're going to map into at the beginning. And there's famous counterexamples where if you skip the mod p, you can actually get some pathological behavior. Okay, so you do ax plus b modulo a large prime number. Doing things modulo prime numbers, it's a field mathematically, so it's just very well behaved. And then you do modulo k because you want one of k slots. Okay, and you know, in the other class, we always give this as an exercise. It's not too bad to do, and it's a good exercise of ideal hash functions. But I won't do it today. I'll focus more on using hash functions and that kind of intuition. Okay, but the point is, you know, if you just have this much more modest requirement, which certainly is true of every ideal hash function, but is not nearly close to capturing perfect randomness, then ax plus b is fine. Okay, ax plus b is obviously super fast, super easy to write down, right? You can even write this code yourself. Okay, so I think that's one thing to point out, is that the hash functions you're using aren't perfectly random. Okay, in fact, perfectly random hash functions aren't practical. Okay, but they're going to often behave like it in critical ways. Okay, so that's going to be our approach. We're going to have some hash function. Okay, so just to make it a little bit clear, I don't know if I said it out loud. A and b are chosen randomly. Okay, so at the point you make the function, you sample a and b, and then your function will use the same a and b forever. Okay, but when we do analyze things, we assume the adversary generating input can't see our choice of a and b. So for any particular input, then we sample a and b and move on. Okay, so you can still take this expectation stuff. Okay, so that's going to be our general approach. You know, we're going to look at our huge space, and we're going to try to assign things to a smaller array by choosing a hash function to do the assignment for us. And the hash function will maybe just be a universal hash function like we did before. Okay, I only mentioned there's things like pairwise independence, three-wise independence, things like that. So there is, you know, a stronger family of hash functions out there. Each time the hash functions get a little bit bigger and a little bit nicer from an analytical perspective. Okay, so there's some trade-offs. Okay, there's something down here. Okay, so good. So the general scheme is that we go from big space to small space and assign things in a small space. And we're hoping that as long as h behaves like a really random function, these will kind of be spread out in your smaller space. Okay? And the basic issue is, well, you're going to have collisions. Okay? And the main algorithmic design question is, how do you deal with collisions? And so there's a variety of different hash tables. that have different strategies. So I left the space open since you might have some ideas. What are some ways of handling or even avoiding collisions? So you have two keys that collide. What do you do? Or how do you kind of try to make sure it doesn't happen? Okay. So in other words, the idea is that, so you get a lot of collisions here. Okay. So now you have a bunch of keys colliding here. So then you make another hash table for these keys. Okay. And if they collide again, you might make another hash table. Or you might just try to make this one so big so that the odds of colliding go down, but you don't have to make it, I mean, it's big relative to a small number. So maybe the overhead isn't too much. Okay. Sure, that's one approach. Other ideas? Sure. So now we can have different data structures like a tree. Okay. In fact, one we're going to discuss today is even simpler. It's just going to build a linked list. Okay. Any other ideas? Yeah. Ah, okay. Yeah, just like abort mission, rebuild. Yeah. Which can be applied to sort of as a second layer on top of any of these strategies. Say, okay, we were just too unlucky. Rebuild. Okay, so here's a fun one. It's called cuckoo hashing. So in this one, what you do is you have two hash functions. So every point is going to have two hash codes. Okay. And what you do is you take your key and you check the first hash code. And if this slot is already occupied, you try the other hash code and see if you can find an empty slot. Okay. And if this one's already occupied by someone else, you might take this someone else and bump him out and see if you can try the other hash code for that person you bumped out. Okay, so they're just kind of bumping each other out. But if this kind of eventually stops and everyone finds a home, then now you only have to look up two hash codes at most to find your key. Try the first one, it's not there, okay, try the second. It's called cuckoo hashing. Okay. Another one called linear probing. So this will only have one hash code. Okay. And so the idea is, so you're here and it gets hashed here where there's a collision. Okay. And now you're going to go here and you're going to start walking to the right until you find the first empty slot. Okay. So you don't have to build any auxiliary data structures. You just look for the next empty slot. And then later when you're looking things up, you're looking this up, you go to that slot and you just walk until you either find your key or you find an empty slot. Then you know the key's not there. Okay. In fact, that's probably the most practical one. And yeah, so maybe it looks something like this. This is a very clever thing. I won't teach it, but it's a very nice proof. Um, and as far as I understand, this was the original implementation of hash table because at some level it's the easiest to code up, right? And that matters in the 1950s when you're stuck on vacuum tubes, right? Because you can just walk down and look for your thing. Okay. And as far as I understand, when I watched some interview by Donald Knuth, the first thing, who's one of the forefathers of algorithms, the first thing algorithm he really analyzed was linear probing probabilistically. And he showed, okay, if the hash function was ideal, then he got very, very good bounds for this. And so he thinks that this might be the first algorithm to ever really be analyzed in up to a certain amount of formal detail because it was just so long ago, right? This is like 50s, 60s kind of thing. Okay, so we've been using linear probing forever. As far as I know, it's still also maybe the because at some level, a lot of these get good, similar asymptotic, big O bounds. And what wins out is just, it's so fast for the machine to walk through an array. You don't get any, cache misses. You just march through. So this is very CPU friendly. Okay. Good. Good. So, but today we're just, beginners. So we're going to start with the most basic one, and get some practice with hash functions. So, so this is chaining. This is the linked list approach. So, the first step you do your ax plus b mod p mod size of the array, and you hash things down. And now, when you get or you do that, and then you do mod m, which is m is the size of your array. I kind of switched from k to m on you. Sorry. And and when you get collisions, we're just going to have a linked list. Okay. So in general, when you do a lookup or an insertion, because even if you're inserting, you have to walk to the bottom of the list. Your running time is going to be proportional to what is the length of the list, for that key. And that's what we're going to analyze. Okay, so this is the simplest one. Probably a lot of real implementations out there use this because it's so simple. Okay, good. So let's try analyzing one of these things. So again, keep in mind that we have a universal hash function, which only has certain properties, right? So universal hash function means any 2 points, they're going to collide with probability 1 over m, where m is the output size. Okay, I should have written it here, but for some reason I didn't. Okay, so given that you're using a universal hash function, the claim is that in expectation, if I'm inserting or deleting a key, I have n total keys and m slots in my hash table. The running time is going to be 1 plus n divided by m in expectation. Okay, so if I make my output array of size m at least as big as the number of keys, it's constant, okay, which is good. Okay, so how do I analyze this? So I'll get us started. Suppose I'm inserting, key I. Deleting and lookup is the same thing. So suppose I'm inserting I. So the claim is it's supposed to take 1 plus n over m time in expectation. Okay. The 1 is just coming from computing ax plus b. Okay. The really interesting part is I want to argue that the length of this list, where I goes, is n over m in expectation. Okay. The 1 is there because otherwise if m is much bigger than n, it looks like you're spending 0 time, and that's not true. Okay. So, okay, how do I prove this? You guys know how to do this, so. Okay, but how do we argue that the list is on average n by m? Remember, you don't have an ideal, perfect hash function, right? You have a universal hash function. So, but anyway, how do we still prove it? We need to analyze this, right? How do you write it down? Yeah, okay. So there's like a buzzword that's the answer for almost everything we'll cover related to randomize, which is okay. So I want to do something like linearity of expectation. So that's some sum of terms. So what am I summing over? Yeah, so the length of the list is how many other items I collide with, right? So maybe I'll make a variable for each one. I'll make xj is equal to 1 if, I don't know, I'll write like k sub j for the jth key, okay, is equal to hi, so that means it collides, okay, 0 otherwise, okay. So summing up over all n, say, other keys. Xj, that's the number of other elements that's colliding with the thing you're inserting. And that'll be the length of the linked list, right? And we want this in expectation. So as you have said, we can apply linearity of expectation, right? We can apply linearity of expectation even though we're using a very crude ax plus b, right? There's lots of dependence here. Ax plus b is not very random. Good. So now we need to analyze just one of these terms. So what is the probability of, so I have key I and key k sub j, right? I have two keys. And what are the odds they collide? 1 by m, right? Because that was just a definition of a universal hash function. So that'll give you your n by m. Okay. So what's really great about this, and again, what's really so great about linearity of expectation, right? All I knew about ax plus b is it had this universal property. The odds of any two things colliding were 1 in m, right? Which of course does take a little time to show for ax plus b. But in general, ax plus b is far from a totally random function. You only have two numbers defining it, right? And we know that you need n numbers to really define a fully random function, right? This is hardly random. It's like bare minimum random. But somehow linear expectation just lets you go right through it and you don't mind these deficiencies. Okay? And so you get this good average case performance, and linear expectation is doing all the work for you, right? And linear expectation itself is like not a difficult thing to prove. So really it's the word expectation and focusing on the average that does all of the work, right? It's only because we're focusing on average that we get this otherwise very practical running time. Okay. All right, any questions? Okay, so let me spend the next time then introducing our next topic and trying to get you appropriately excited. Okay, so I know the web page has changed a little bit since, but who's seen this before? Okay, so this is the Google Trends website, and it'll tell you well about trends in Google search. Okay, I guess someday we'll have a ChatGPT trends. So this must have changed, but I guess this panel here is going through all the states and saying who is searching for Kim Kardashian more or Taylor Swift more. And at the time of this, which was clearly years ago, it seems like Kim Kardashian went 50 for 50. Okay. People who are searching the World Cup, people who are searching football or American football. Oh, so I guess California likes soccer more than, okay, whatever. Okay, and then at the time, they have things like this, like recently trending. I mean, you also see this on the right side of Twitter and stuff, right? So you can sort of figure out when I made the slides based on this. So I guess Don't Worry Darling just came out. If I remember correctly, do you guys watch basketball? So Chet Holmgren just got drafted and he played this summer league game in like Portland, and LeBron James just ran him over and he was out for a year. So that was roughly when this happened. So I think it was the end of summer because this was for a randomized class. It was first week of class. I think Nick Cannon had his like 100th child or something. And I guess there was a soccer game, okay? So these are kind of things that are a little bit higher than usual, right? Anomalies. So, okay. So they do this, they're keeping track of these queries, not just to make this silly website, right? They're doing this anyway for caching, okay? Why is Google so fast? How come when you ask a question, it can search the internet and answer your question so quickly? It's because it doesn't search the internet when you ask a question, okay? When you ask a question, so did a million other people, and it already is saved in some database, okay? So when you just feed it one of our word problems and ask, is this a DAG or something, all your classmates already did, and it's been cached, right? So, so caching is really important. So keeping track of, like like 99.9999% of traffic is coming from like 0.0001% of possible queries or something, right? So if they can just keep track of what are these important ones, okay, you don't have to do this live stuff, right? So, but then there's a question of like how? How do you do that, right? Because everyone's using Google. There is still a diverse amount of queries out there, right? And there's way too many different queries to maintain a counter for every single one, right? You don't want a counter for every single possible query, right? It's like, oh, my mom introduces yet another brand new novel typo, and they're not going to start a new counter for this, right? So that's, a basic thing, right? And you can imagine caching is useful in many other cases. This is just, a little bit of a story. So, good. So this is maybe a more formal version of the problem, okay? So we're going to do, just for this lecture, a slightly different computation model that you haven't seen before, okay? And so it's called the streaming model, and it's one way to model situations where the data is huge, okay? So the idea is that the data is too big to fit in a computer, okay? So we're going to imagine that the elements come one by one in like a stream. Okay, you just like plugged into the internet, the elements are coming one by one. And in general, your computer cannot save all of the data. Maybe it could save like a little more than one data or something, but it cannot save anything proportional to the size of the entire data. Okay. And so the idea is that each time step, you get to see another number, another number, another number, another number. Just another search query, another search query. Maybe I'll just make it small so it's less confusing. So just one at a time, one at a time. And you can maintain a little extra memory. Okay, but nothing proportional to the size of the input, one by one, one by one, one by one, one by one, one by one. Okay. And we'll say that an element is a 5% heavy hitter, 5% chosen arbitrarily, if it appears at least 5% of the time. Okay. And we're going to replace this with some parameter epsilon. Okay, so Google might be interested in epsilon is like 0.0001 or something. And good. And our goal is to try to identify all of the elements that occur, beyond a certain threshold in the stream. Okay, so this is the heavy hitters problem. Okay. Good. So our goal is to try to identify all of the heavy hitters in sublinear space. Okay, so that could be like squared n, that could be like log n, that would be really great. Probably, constant might be too much, something like that, right? So anything dramatically smaller than the total number of elements is already interesting because that's better than maintaining a counter for every element. Okay, good. So that's the idea. Okay. Good. So on the face of it, this seems impossible, right? You're giving up information just by, requiring yourself to use less than n space. Okay. But there are some glimmers of hope, and I wanted to see if you have any suggestions. Right? So you should clearly be like, well, you're not counting everything. How can you do this, right? So we're going to try to get over some of these basic obstructions for the sake of yeah. Like what? Okay, so something like least recently used. So the stream could be adversarial. So it can play tricks on you to screw up your least recently used strategy. That's another issue. So the stream will actually be adversarial. Or we won't assume the stream is like coming in random order from a fixed distribution or something, which would actually be easy because you just sample and you're done. Okay. But remember, Google Trends is like interested in anomalies, right? It's interested in changes in the deviations from the distribution, things like this. Right. So that's not quite it. Well, so it is true the input is much bigger than the memory we have, which is a bit of an issue, right? But if my goal is to identify just 5% heavy hitters, what's sort of like the size of the output? put alternatively, how many 5% heavy hitters can there be? Less than 5% of the stream? 20. There can only be 20 because each one occupies 5%. Okay, so that's already a good start. We only have 20 things we're trying to identify. So if we have less memory than that, then we'd be really screwed, I think. Okay. All right, another one is we're going to relax the problems in two directions. Okay, one is we're going to use randomization, which you might have expected, but that means there's going to be a small chance of failure. Doesn't have to be perfect. Okay, all the time, that is. And then the other one, is we're going to approximate, and I'll define that either in the moment or next time. We'll allow some amount of margin of error. As long as we get most of the heavy hitters, or we get all the heavy hitters, and maybe we accidentally include some 4%, 3%, pretty big, but not exactly heavy hitters, we'll have some margin of error. Okay? And that'll give us a little bit more space. Now, this will relax the model, make things more plausible, make things feasible. That wiggle room is what we get to exploit algorithmically, but we're not going to lose any of our rigor or worst case bounds. This will be proven rigorously. Our error probability will be proven rigorously. We won't make any assumptions about the input. Okay, so it'll still be something you can reliably use. That's the most important thing. So maybe that's a good place to stop. Yeah. So I'll stop there. And so that's what we'll do next time, okay? And maybe the cool thing is you already have all the tools, like it'll just be reusing the things we've been using, union bound, linear expectation, things like this, to pull off what I think is a pretty cool thing. When I first learned this, it blew my mind, okay? So that's what we'll do Monday. All right, thank you. All right, so this is the second half of this lecture on hashing and heavy hitters. Last time we did hash tables and implementing dictionaries, and I introduced the heavy hitters problem, trying to get you all excited. So let me quickly remind you. So one of the motivation is Google, among others, want to, for example, keep track of what are the most frequent queries, and a big reason for this is for caching, right? If they actually know what are the popular queries, and they can start pre-computing stuff ahead of time, and essentially turn online problems into offline problems and things like this. So our streaming model in the heavy hitters problem is you're seeing a bunch of elements that are appearing one by one, and we want to think of the data being so big it can't all fit in our computer. So instead of something like this, you'll have a small window like this. And you can see the current element as it comes into stream, and maybe you can keep a little bit of extra info, but not proportional to the input size. This is the only time this will come up in this class. One of my goals is just to expose you to this kind of different model of computation, which I think is practically motivated, but maybe something you hadn't considered. So in the heavy hitters problem, I want to find all the problems that occur, say, at least 5% of the time. And we want to do it again. The interesting part of the problem is the space constraint. I want to use something that's essentially independent of the number of elements in the stream. I want to do better than counting everything. So square root n, while that might still be big for Google, is still a big improvement. In fact, you can fit 1 billion numbers in your computer, so 1 billion squared would actually be fine, probably, right? So, okay. So this might sound impossible, right? How can you get all of the heavy hitters? And at some level, be trying to count everything without having enough space for counters. So we're going to take advantage of 3 conceptual things. The first basic thing is, okay, if you only want to report the heavy hitters, yeah, there's many inputs, but there's kind of only 20 outputs, right? There's a very sparse solution. So that at least gives you some hope that you can use space proportional to 20, proportional to the output size, instead of proportional to the input size, which is infeasible. Next, we'll do some randomization. It won't be too much randomization, since the whole point is we're only just getting exposed to it. And our algorithm will have some small chance of failure. Okay, so as soon as you start, letting loose the controls on doing things exactly, you start opening up a lot of wiggle room. And second, we're going to allow a little bit of error. Okay, it's going to be controlled. We're going to bound it. We're going to have trade-offs. So you'll still get like worst case rigorous stuff, things that you can actually use. It's not like a heuristic. Okay, but you'll see algorithmically how allowing for a little bit of error lets us get away with stuff that we shouldn't. So good. Now this lecture we're going to use for the first time Markov's inequality. So I'll just briefly remind you. This is saying, for example, that at most half of the class can get twice the average on the midterm, right? Because if more than half the class got twice the average, that would force the average to be even higher, right? So in other words, this one, it might look mathy, it is expressed mathematically, but it's totally common sense. It's not surprising that at most half the class can get twice the average on the midterm. Okay, so just think of it that way. It'll come up at some point. Okay, so let's go into this. So this is our model. And we're going to replace that 5% with some parameter epsilon. So 5% would be like 0.05. It would be between 0 and 1, where 1 is like 100%. Okay? But you can just think of epsilon as 0.05 any point through if you're uncomfortable with the variable. And we're actually going to work on a slightly related problem. So as opposed to identifying the actual 5% heavy hitters, we're going to instead look at this related problem of trying to estimate the frequency of every element, maybe up to 5% error or something like this. Okay? So the total absolute frequency for a particular element X is how many times it appears in the stream. So that could be a huge number. It could be 0. That could be as big as m, the length of the stream. And the relative would just be dividing over the length of the stream. So that's the percentage. Okay, so relative frequency of 0.01 would be 1% of the stream is this element. Okay, so clearly if you knew all the frequencies, then you knew all the heavy hitters. So, right. So an epsilon heavy hitter corresponds to a relative frequency of epsilon. Okay, so if you can identify all the elements with relative frequency epsilon, you're good. And if you can kind of estimate, if you can estimate all the frequencies up to say plus or minus 0.1 epsilon, then you're going to roughly be able to identify the heavy hitters. Okay, because you'll identify everything that's at least like 0.9 epsilon or something. Okay, so we're going to try to focus today on just estimating the relative frequency up to epsilon error. If I had done this lecture a little earlier in class, it's a typical exercise to take our estimating the frequencies and turning it into an algorithm that actually will gather and output the heavy hitters. Okay, in one stream. So in one possibility you can do is you can do 2 passes over the data. The first pass counts everything, and then you just look into your table or something on the second pass. But with a little bit of thought, you can do it in 1 pass, and that's often an exercise I give just as are you used to comfortable with the bounds, and can you play with it? And yeah, not too complicated, just kind of a sanity check sort of exercise. So that might be fun to think about. But directly, we're going to try to estimate the relative frequency. Okay, good. So we want to estimate all the relative frequencies up to epsilon additive error. So I really want to maintain a number for everything, right? But obviously, we can't have a number for everything. But there is one piece of good news, right? If I want epsilon additive error, then maybe it is possible the output could be small. But the question is why? Yeah, so if I just looked at this and said, oh, you want to estimate all the frequencies, right? Like, oh, shoot, I have to have a counter for everything. That's impossible, right? So the output would seem huge, and it would seem impossible to do this. But I'm saying that if you're allowing for epsilon additive error, then I can argue that implicitly, at least, the output could be small enough to fit on a computer. So really, you just want a data structure that's able to say, oh, here's an element, you return a number, right? So you don't actually have to have all the counters explicitly. So basically, I'm saying that for this problem, there's always a sparse solution, a solution that can be expressed with very little data, not course, not proportional to the number of elements. So I'm just thinking about the output, not even the algorithm, if that makes sense. So before we remarked that, oh, there's only so many heavy hitters, you could actually have the whole list potentially, right? That gives you some hope. I want to do something analogous for this. So you're allowed 5% error or something. Okay, so, there's maybe 1 over epsilon heavy hitters, so maybe you can keep track of all of those. Let's say you even knew the heavy hitters, right, for some magical reason. You know after everyone was value at least epsilon. So those counters, maybe you need some counters for each one. But what about an element whose frequency is epsilon over 2? Or just 0.00001, very close to 0. So for most, for most of the elements, all but a few big ones, 0 is a good estimate in this regime. Okay, so there does exist, sparse solutions that will fit on a computer because I can output 0 for all but a few elements, and it will still be okay within this regime as long as I allow this epsilon additive error. Right? So this basic kind of argument you can't do if you're doing things exactly. If you're doing things approximately, oh, okay, things are tractable. That's the only point I'm trying to make. Right? Okay, so good. Of course, the problem is you don't know which elements to count. If you knew which elements to count, you would just reserve a counter for each of the heavy hitters, count those, and then just ignore everything else and output 0. Right? That would fit and take 1 over epsilon space or something, 1 over epsilon counters. Okay. So the real predicament is sort of how do I sort of estimate things without knowing what I want to estimate? Yeah. I want to heighten this because I think it's impossible to do without randomization. Okay. So, I was going to give you a chance to guess, but does anyone want to guess that wasn't paying attention for fun? Or even if you saw it, okay, we're going to use hashing. Does anyone want to try to guess ideas using hashing? Okay. All right, so what we're going to do. So we have n elements. We want to sort of estimate counters for all of them, right? Well, we could only have a few counters. We only have space for a limited number of counters. 1 over epsilon would be ideal. So what are we going to do? We're going to allocate maybe a constant factor bigger than 1 over epsilon. I chose 10. Probably 2 or 4 would be fine for analysis. I just made it extra big. Okay, so I'm going to allocate a few extra counters, but something proportional to 1 over epsilon, which is sort of the target. Okay. And now from here, what we're going to do is, the ith element, I'm just going to hash it to one of these entries. Okay. And I'll use that, those limited independence universal hash functions like we did last time. Okay. So ax plus b kind of thing. So we'll just kind of hash everything down. So this counter here in the bottom left is going to be the sum of all the counts from all the elements that hashed in. Okay, so you're going to get bigger numbers down here, but only 10 over epsilon of them. Okay. So what's the intuition? Or consider an extreme case, right? What if like even though there could be many elements, there is only 1 over epsilon elements that got any ever appeared in the stream and they just were all heavy hitters, right? So you have this really sparse thing. It's just 0 everywhere. And then what are you kind of hoping happens? Okay, so if they collide, then their counters are going to be like adding up, right? Now, okay, so for example, so in that extreme case, you know, maybe epsilon is 33% or something. There can only be 3 big elements. And let's say the entire stream is just the 3 big elements alternating. Everything else is 0. You're hoping is that if those 3 don't collide with each other, right, and they all get hashed to their own counters, okay, then that counter that it gets hashed into will actually be the right number, right? So you're hoping, okay, in one extreme case, if there's only actually 3 elements that actually appear in the stream, then they won't collide, and this will just preserve the information exactly. Now, in general, say this point goes here, and you're going to get this, plus you're going to get a lot of noise, right? So other elements that hash in are going to, add a little bit to the counter, add a little bit to the counter, right? So if I said, oh, what's the counter for this thing? And I look down here, I'm going to get an overestimate because I'm going to get its actual count plus some noise, right? But if this thing was totally random, you're hoping that the noise is going to be averaged out. And the average noise will look something like epsilon over 10 times the stream, right? And you're allowed epsilon additive error. So the average noise is well within our margin of error. So intuitively, every element is going to have its own count plus some noise from other elements colliding. The average noise, if I took the whole stream, which is maybe length m or something, divided over n elements, only 1 over w fraction, that's epsilon over 10 fraction, should appear in the same slot, adding noise. And we're allowed epsilon error, let alone, and this is just epsilon over 10. Okay, so the average noise is much smaller than our bounds. That's the high level intuition. Okay, now you might still be wrong because you can get unlucky, you get a lot of noise, and that's where we actually need to analyze things. Okay, so good. So right, so to return the frequency of an element I, we're just going to look up the counter, for that element. Okay, so we're always going to be overestimating, and the only question is, did we overestimate by too much, by more than epsilon? Okay, more than 5%. Okay. Okay, so some notation. I guess I'm letting A denote the array of counters. Okay, so that's 10 over epsilon or something. For each element I, I'll let Fi be the true frequency of the element. And H will be our universal hash function. That means any 2 inputs will collide with, 1 over W probability. And M will be the total length of the stream. Okay, so the relative frequency will come from taking this quantity and dividing by M. Okay, so when you look up an element I, or any particular point in the cell is going to be adding up for all the elements I that hash to this spot, that frequency. And that's just kind of expressing as a sum. Okay, so good. All right, so here's our claim. Okay, so let's take a particular element I. Okay, and our estimate is go to the hash location and return this counter, which is a sum of things, right? And our claim is that the true frequency is at most the estimate, and with probability at least 1/2, at most the frequency plus epsilon over 5m. M is the total length of the stream. Okay, with probability 1/2. So half the time, you're going to get a pretty good estimate for element I. for this particular element. Okay. So the first inequality is just coming from the fact that the collisions are only overestimating. Okay. So the interesting part is the second claim, the claim that, okay, I know I was going to overestimate because things are colliding, but half the time I'm not going to overestimate by all that much. Okay. So how do we analyze this? And in particular, what might be a good first step? First, does the claim make sense? I know it's a lot of notation coming at you fast. Yeah. So the greater than equal, the overestimate part is probably okay for everyone because an element I, you have your own count there, and you have some other elements colliding that can increase. The interesting part is, okay, how much did I go up by? I'm saying, oh, at most an epsilon fraction, epsilon over 5, with constant probability. Okay, so sometimes we'll get a good estimate. Okay. So what might be a good first step in trying to analyze this? Like you're interested in this, right? This is a random quantity. Well, if you have any random quantity, what's a good first question? Yeah, or just what's the expectation, right? I tell you there's some random thing. First you might ask what's the average, right? Oh, here's a baseball player. What's the batting average, right? Okay, so let's figure that out first. So the expected value of AHI, okay, which is summing up over all coordinates, I guess I'll call it K, where HI is equal to HK. So all objects with the same hash code, including I itself, the frequency f sub k. Okay. Now you could write this a little bit differently. So I'll write sum over k xk, where xk is equal to the frequency of element k if the hash codes are equal. They got hashed to the same slot. 0 otherwise. Okay. So I'm just kind of taking some information from under the summand and kind of packing it into the variable here. Okay. Okay. Why? So what's the next step? Yeah. So the reason I introduced xk was to just get it into a form that you can apply linear of expectation to, because you can't apply it really directly to this because there's information encoded in what you're summing over. Okay, so that's one slightly tricky thing, but okay. Okay, so now let's just look at one of these xk's, right? So I can think of two different cases. One is when so k is an index of another element. So k could be either equal to I, the element we're interested in, or not, right? So if k is equal to I, so if this is the same element, then what is xk? It's always fi, right? Because you always collide with yourself. So that's not too bad. So you always have an fi term, and now we're just interested in the remaining elements that are not equal to I, and we want to figure out the expected value of xk, right? So you have another element, and if it collides, you add fk. If not, so what is the expected value of xk when k is not the same as I? It's the contribution to AHI. So K is another element. Because I don't know why I felt like I used up all the J's. So instead of J, I use K. Okay. So we're looking at a particular element I, and this is the number you would report, right? You would go to the slot that I is hashed into, and you report this number. And this number consists of Fi plus a sum from other elements. Okay. And we're just trying to figure out what it is in expectation. So another element, this is its contribution. If it collides, it'll add Fk. That's the frequency of element K. If it doesn't collide, it adds 0. So on average, how much is it adding? Exactly. So you just have to figure out the probability of it colliding. And what are the odds of it colliding? Yeah, 1 over W, I think. Yeah, 1 over W, the number of arrays we have down below. W was set to 10 over epsilon. So 1 over W is epsilon over 10. So this here will become epsilon over 10 times the frequency of that element. And then all the frequencies added up is at most m. Okay, that's the length of the streams. So you get f sub I plus epsilon over 10 m. Okay, so all this is really saying is that the average noise is epsilon over 10 m. Okay, good. Now, did I leave myself any space? No. Okay, so now I want to try to. Okay, so the average is actually better than what we want, right? Because we want epsilon over 5m. This is epsilon over 10. But actually, this claim is a little different because it says there's probability at least 1/2 the excess error is at most epsilon over 5. Okay, so so what have we done? So I'm going to erase a little bit just to make space. Or can I shrink it maybe? That's not good. Okay, so all right, so we know this. An expectation the sum will return is what we want, plus epsilon over 10m. I want to argue is probability at least 1/2. It'll be at most epsilon over 5m. I use Markov's inequality. So, actually, there's one thing a little bit subtle, which is this. If we look at this difference, remove this. Okay. So if I take out the return value and I subtract my own counter, this is always at least 0 because it's always overestimating. So this can be your variable for Markov's inequality. So we know that the expectation of this thing is at most epsilon over 10m. Okay. So the expectation of this is at most epsilon over 10m. So then the probability of that thing being at least epsilon over 5m, that's 2 times the average, is at most 1/2. Okay? At most half the class can get twice the class average. Okay, good. Making progress? So, good. So what we now showed is that for every element individually, you'll get a good estimate with probability 1/2. Right? You'll get error epsilon over 5 or something half the time. But what we want now is a little bit different. We want to estimate all the frequencies with high probability. So we want to take that 1/2 and somehow put it on steroids. I want to get that 1/2 really good, and I want all the elements to be good. Okay, so, right. So any ideas? Okay. All right. So here's some stuff, you know? All right. Imagine I repeatedly flip a coin, right? What's the odds that the first coin toss is tails? Like I want to get heads, right? 1/2. And it's like, okay, now I have to throw another coin, right? What are the odds that both of the first two are tails? 1/4. Okay, so there's some decent chance of this happening. What are the odds that I throw 100 coins in a row and they all come up tails? 1/2 to the 100, right? That's never going to happen. Okay? So probability plummets. 1/2 and 1/4 doesn't seem very big, but you just do it 98 more times and this is, effectively zero. So, okay, so there are ways to sort of get our probability down, right? Think of this as the probability of our error, of our algorithm screwing up, right? I want to get it down to 1/2 to the 100 or something like this, okay? But I have something that makes a mistake half the time. So what can we do to improve the error rate of our algorithm? So currently our algorithm just makes one hash table and one hash function and estimates things. And it'll be right, yeah. Yeah, we're going to make a ton of these. Not a ton, we'll figure out how many. So we'll make D copies of this. Okay, oh, gradually things appear. Okay. So we'll make D copies. Each of this has its own hash function. It's running the same experiment. Okay. So the total space of this new data structure is just going to increase things by a factor of D, right? Originally I need W counters, now I need W times D. I chose D for depth, but whatever. Okay. Now, if you have all of these estimates, if I want to look up a particular element i's frequency, and I have all these tables built up, what should I do? You can average. You can average. That's probably the most natural thing. You can actually take the lowest one. So in this case, because our error is only overestimating, the best estimate you can get is the smallest one. That's going to be the closest to the truth. So averaging works, but actually here, minimum is easier. It's going to be easier to analyze as well. Average, we'll have to use something kind of like the central limit theorem. But here, you're going to see that the minimum is going to be easy for us to do without too much overhead. Okay, so we're going to return the minimum, right? Okay, I blew it. That's okay. So the minimum is a bad estimate if and only if all of them are bad. But each one is bad with probability 1/2. So it's like flipping all these coins and they all come up tails. That's 1/2 to the D. Okay, so once you got one-sided error, you can just duplicate this thing and you're only wrong if they're all wrong. Okay, so this is a very favorable, this is a very practical thing, right? You might imagine other situations, keep an eye out for situations where you can just duplicate and get your error down for free. Yeah. It'll increase a little bit, but actually, you won't get this. W could be. So Markov's inequality is just going to say like, so if I increase W, I can get the average down from like, if I increase it by a factor of 10, before it's 10 over epsilon, if I made 100 over epsilon, the average error will be epsilon over 100. And the odds of exceeding epsilon over 5 will be like 1 out of 50. So if I increase this by a factor of 2, our error analysis from before will go down by a factor of 2. So if I double the space, it only goes down. If I multiply 100, it only goes down by a factor of 100. Here you're actually multiplying things together because you're getting this and. You're getting this geometric decrease. That's a good thing to keep in mind, right? So another strategy would have just made W bigger. And if you work it out, you're not going to drop your error rate faster. Right? So there are differences. So keeping an eye out for these things that I think are practical. Okay, good. So if we set D to be something like log n, 10 log n, right? And I take 2 to the 10 log n, any particular element, there's n elements, is correct with probably 1 over n to the 10. Right? Super small, especially for a large n, which is what we're interested in. Okay. Good. So now the question is, so any particular element is almost certainly correct. But I want all of the elements to be correct. How do we do that? They're not independent. The errors are not independent. It's like linear expectation, but there's another thing we've used before. Union bound. Yeah, so there's basically two main tools we use to deal with lack of independence. One is linear expectation. That's good when you're computing averages, and union bound when you're trying to avoid all of bad events happening, right? So one bad event is one of the elements is bad, and you aren't trying to avoid any element being bad. So hopefully it's written ahead of time. Yeah. So the probability that some element is bad is always bounded above by summing over all the elements, the probability of it being bad, right? But there's n elements, and each one is wrong with probability 1 over n to the 10. So this quantity here, right, will come out to 1 over n to the 9. Okay, so you're getting this really favorable trade-off from duplicating, right? And so it's not much effort to get the probability of error so low, you can easily, union bound have plenty of, leftover, small values. Okay, so this is very practical. Okay, good. Any questions? The last thing we'll ever see lecture-wise on randomness. I think there's some concluding slide. Yeah. The total amount of space at the end of the day was just log n over epsilon, assuming each counter takes constant space. If you want, you can have another log n for the counters. Yeah. So you're plus or minus epsilon. So if epsilon is 0.01, you'll return some number that could be off by 0.01. Yeah. In which case, 1 over epsilon will be 100. Okay. Cool. Anything else? Okay. Oh, yeah. Okay. There was another second. This is nothing new. Okay. Good. All right. That's it. So then let me use the remaining time.